Hello, everyone. My name is Asier Ozaeta, and I'll be talking today about quantum optimization with QAOA. So Fabio has talked previously about BQE, one near-term algorithm, and now we'll discuss QAOA, another near-term algorithm. So the idea of this talk is first to introduce what QAOA is, then say why should be interested in this, then explain how it works, and finally show an example of QAOA using the QC Ware platform. All right, so let's get started. So QAOA stands for Quantum Approximate Optimization Algorithm. It was published in 2014 in the archive. And the authors are Edward Farhi, Jerzy Goldstone, and Sam Goodman. For those of you who are interested in this algorithm, Edward Farhi will be giving a talk on day 3 on the optimization track, so don't miss it. So why should we care about the QAOA? Well, I have 4 points to make to answer those questions. First of all, because it solves optimization problems. If we wouldn't have that one, then we wouldn't care about the other 3. Next, because Nearterm is a near-term algorithm that we can fit in current hardware. And third, because it's an adaptable algorithm. And fourth, because it's expected to be faster than classical. Let me elaborate on each point. Let's start with the first one. Here, I saw some examples of some sample problems that we can tackle using the QAOA algorithm. And we have industrial, financial, travel and transportation, energy, et cetera, et cetera. Below each, for example, for financial, I show 2 examples of problems that they've been proven to be able to tackle with QAOA. For example, portfolio optimization and trade settlement in the financial case. So this is very important. QAOA solves quadratic and constrained problems with binary variables. That's what QAOA does. And the question here is, so what happens if the objective function that I want to optimize is not quadratic and constrained and doesn't have binary variables? Well, if you have a function, an objective function that is higher than quadratic, you can always transform that to quadratic by adding ancilla variables. If you have continuous variables, well, you'll have to discretize those and show them or represent them using the binary variables. What if you have constraints? In that case, we are able to represent those constraints in this form in a simple manner. So that wouldn't be a problem. Second point, it's a near-term algorithm. We have discussed in previous sessions what near-term algorithms are, but let me reiterate and say, what is this all about? So near-term algorithms run on small quantum computers. They are low depth, which means that the qubits that we are using shouldn't be very coherent. We don't require much coherence to make this algorithm run. Also, this means that we don't require as many quantum gates to represent this algorithm in a real quantum hardware. It's also robust to errors, which means that it shouldn't require much error correction, or any, and requires relatively few physical qubits to get to interesting practical problem size. Related to this last point is the last one, the efficient use of qubits. So it just needs enough qubits to store the problem. So one variable that we aim to solve, or that we aim to optimize, corresponds to 1 qubit, which is in principle difficult to improve. It's also an adaptable algorithm. This means that in principle, we can easily model the objective function that we want to optimize using this algorithm. And finally, it's expected to be faster than classical. This relates to the point that Wim was making before, and let me elaborate on that a bit. So the idea here is that we're comparing two things, a classical approach and a quantum approach. And here I saw two pictures that more or less represent what's happening on each approach. So in the classical approach, we move through the search space one solution at a time, while on the quantum approach, we can create a superposition of states in which we can operate in parallel. This is the intuition that we have about quantum. This is, of course, a very rough understanding of what's really happening on quantum algorithms, but it's a starting point. Next, in the next slides, I'll be explaining in detail what's happening in the QAOA algorithm, so you will be able to understand what's really going on. So hopefully I convinced you that QAOA is something that you should care about. So let's talk about optimization using QAOA. So in classical approach, we usually reduce the search space of our problem to be able to solve it more efficiently. The idea with QAOA is that we don't need to do that. So we just take the whole problem and we solve it as a whole. That means that we maybe don't have an improvement in the runtime that it takes to solve the problem, but we have an improvement in the solution that you're getting, because you're able to search in a bigger space. Here I saw a quote from Scott Aronson, and it relates to 2 points that were made before by Peter and Adam. So this is a quote by Scott Aronson, taken from his blog. This was posted when the QAOA archive paper first came out. And it says, the first time that a quantum algorithm has been proved to achieve a better approximation ratio for a natural NP-hard optimization problem than the best known classical algorithm achieves, which is kind of a big deal, but as you can see just below, there's a caveat, which what happened here was that, okay, some classical optimization guys saw this algorithm and say, okay, this cannot be right, and they tried to solve it better, and they managed. So it was beaten again by the classical community. This is related to one point that Peter was making, in which benchmarking with quantum, quantum versus classical is going to be always difficult, because it's going to be always a competition between those two. There's going to be improvements. There's going to be little tweaks that are going to improve the performance of classical and quantum. So yeah, this is something that we should expect in the next years. Another thing is, what Adam was mentioning before. Remember that there were a few categories in which he placed the different algorithms, and QAOA was in the one that said that the performance was unknown. We don't know how well this performs compared to classical. And what this means is that, okay, maybe right now, using the complexity theory, we cannot say that the QAOA is going to run better or faster than the classical algorithms, but we have to try. We have to check the specific cases, and we have to check how it works for all different problems and objective functions. All right. So what does a QAOA circuit look like? This is a QAOA quantum circuit for 2 interactions. So the number of interactions of a QAOA circuit can be modified to make it as long or as short as we want, with a minimum of 1 interaction. So what we have, we start from the right corner to the left. So we have the input variable models, which corresponds to the qubit. Remember what I mentioned before. One variable that we want to optimize corresponds to 1 qubit. So we have the qubits on the left side that start in the 0 state. What we do in the initialization process is create a superposition of an equal superposition of all possible states for those qubits. So we generate a quantum state in which the probability for all possible bit string solutions is the same. Then we proceed with updating the intermediate solutions with the operators UC and UB. Each pair of operators UC and UB, that I'm not going to explain what they are here, update the intermediate solution and correspond to one iteration. So in this case, we have 2 iterations, which means that we have 2 UC operators and 2 UB operators. When we have applied these quantum operators, the only thing that's left is to read the results and obtain the expectation value for this quantum circuit. So let's see how this fits inside of the classical loop. So again, as Fabio mentioned in the previous talk, this is a classical quantum hybrid algorithm. So it's not just the quantum part that we are working on using QAOA. There's also a classical part. And again, this is very similar to very similar to the picture that Fabio was showing before. You can see that on top, we have the model. We have the objective function that we want to optimize, and that we fit on the quantum circuit using the UC and UB operators that I mentioned before. So you can see there that we have the quantum circuit and the expectation values that I showed previously. That's basically what I showed before. That's where all the quantum part fits. And we have there also a classical optimizer, which can be any classical optimizer that you prefer, because there is still no agreement in the community for which classical optimizer works best for QAOA. So what's happening here is that the classical optimizer is providing the quantum circuit parameters that modify the U operators. This modifies the expectation value. And what the classical optimizer is trying to achieve is a reduction in the value of in the expectation value. So the classical optimizer will feed parameters to the quantum circuit. The quantum circuit will output the expectation value, and the classical optimizer will update the parameters again based on the value that he has obtained from the quantum circuit. Once the topic criterion is obtained, we just get the solution. And that's how a QAOA implementation works. All right, so I told you why. I explained more or less how it works. Let's make an example of this QAOA algorithm. Let's use the set cover problem. For those of you who are not familiar with it, this is the problem definition states given a collection of sets to find the minimum number of sets such that all values contained within this whole collection are represented in the sets we have chosen. Okay, let me explain that in a more clear way. Imagine that we are running a lab, and we want that lab to be guarded for 24 hours because we have very important information, very valuable information there. And of course, we don't want to hire more people that we need because we are in the budget. And we have the following candidates that show there in the picture. Candidate A to E, which are available in different time slots. So the question here is, which candidates should we hire? So we hire the minimum number of candidates, and we still get the 24-hour surveillance in our lab. You can see that here it's pretty easy, and candidate B and candidate E is the answer. But let's see how we model and how we will tackle this problem using the QC Ware platform API, which is what I will show in the next slide. Okay, so the notebook that I'm aiming to show here is quite complex, but I just want to highlight 4 different points, which is the classical model, QAOA model, running the QAOA in Python, and reviewing results. If we could show the first video, please. Okay, so this is just a regular Python notebook. We are opening it. And there you can see quantum approach for set cover notebook. And you can see that there is a table of contents with a bunch of things that the notebook contains. Of course, as I mentioned, there are many details in this notebook that I won't mention. I'll just skip through it. And yeah, I just want to make a few points on this. So first is the introduction, in which we have the problem that I explained before. We now understand what's going on. We want to model this problem, and we want to solve this problem of the lab. Here we saw some math of how the weighted set cover would work. But again, I won't go over it now. If you're interested, you can go over it yourself, because I believe we will make this demo available very soon. All right. So first thing I want to show is how we solve this problem using a classical model. So most of you probably are going to be familiar on how to solve these kind of problems using classical methods, but I still show what we did there. So if we could show that next video. All right, so again, we're at the beginning of the notebook. We'll just click on the classical approach. And for this particular notebook, we use the OrTools library. There's nothing new. There's going to be nothing quantum here. We're just going to show how we do it in a classical way. We just import the libraries. We define the problem. It has 4 different time zones, and we have a number of applicants that have different subsets. We define the binary variables. Then we add the constraints. Next, we set the coefficients, and then we just solve the function and assert that is the optimal solution for this problem. So this is pretty straightforward. This is something that all of you know. But the question now is, what happens if we want to solve it using quantum? So the first thing that we have to do is take our problem and transform it to a Kubo model. What I was saying before, QAOA only solves problems that are quadratic, unconstrained, and with binary variables. So we have to transform the set cover problem to that formulation. And that's what we will show in the next video that should be playing now. OK, again, start with the beginning, and we start with the Kubo formulation. So what we want to do is transform that is up there, that is not quadratic, or it doesn't have the Kubo form, the minimize and the constraints. Remember that we can add constraints to our Kubo form. That's not a big deal. And yeah, in this part, we show all the details on how to do this. We are not going to go over them. If you are interested, again, you can check it, or you can chat with me after. And what we do is, again, we define the time slot. We have 4 time slots. We have a number of candidates that have different subsets of the time slot. And we also need to define a number of penalty variables, because the constraints that are going to be implemented in the Kubo form are going to take the form of penalty functions. We define those, and what we have to do next is define the Q matrix, or the Kubo formulation of the problem. Yeah, we're going to go over the steps. I'm not going to explain what's going on, but basically what we do is define a Q dictionary, Python dictionary, and take the following 3 steps to implement the set cover problem into a Kubo formulation in the form of a Python dictionary. Now we do have our model for our problem. Now we have to just send it to the quantum machine, and we have to obtain the solution. In order to do that, we will use the QC Ware platform API, and that's what I'm going to show in the next video. So if we could play that, please. All right. So we do have the Q matrix, which contains our problem. And if we minimize this Q matrix, we're going to obtain the solution to our problem. So here we see the call we make to the QC Ware library. It has 3 simple values, the Q, the key, which is your password, and the solver you want to use. So in this case, we specify the Google QAOA solver, which is the Circ QA simulator that runs on our platform. It's very easy to change the solver that we want to use. We can switch that to any of the available hardware, and we will run it in different platforms. We're also reducing the length of the solution because we have added some ancillary variables that are not very relevant for the solution that we are looking for. The ancillary variables are only relevant for the processing of the result. All right, so yeah, next we'll play the reviewing results, the next video, where we will show the different results that we obtained. So we could play that. Great, so here we are in the result obtained by the classical solver. We are obtaining the selected subsets, which are B and E. And here we have the solution that we obtained from the QC Ware platform, which is a list of binary variables. Each variable here corresponds to the fact that if we have chosen a candidate or not. So we can see here that we haven't chosen candidate A, we have chosen candidate B, we haven't chosen candidate C, we haven't chosen candidate D, and we have chosen candidate E. Basically, the same solution that we obtained for the classical, but represented in a different form, with binary variables and with one representing the candidates we have chosen. All right, so that's the demo, the implementation of the QAOA that I wanted to show you. I hope that allows you to understand a bit better how the QAOA is implemented, how it works. So one last note. QC Ware has made a Circ implementation of QAOA, so it contributed a vanilla version of QAOA, and it's in the Circ GitHub repo if anyone wants to check it. And we are also working internally in improving this QAOA algorithm inside the platform so it can run better and faster. So just a side note. And this is all I wanted to say. Thank you very much for your attention. So yeah, next we'll take some questions if there are any, and please don't forget to rate. Any questions? Anyone?
You mentioned that QAOA is only useful for QUBO problems.
Mm-hmm.
Well, circuit model QAOA can do K-local Hamiltonians pretty efficiently, especially if they're all on the standard basis made of poly Z's, right?
Mm-hmm.
So that would be beyond quadratic, right?
Yes. Yes. I agree with you. I just wanted to present this in a simple way. This is not a scientific, it's not a scientific talk. It's just about.
Yeah, but it's actually more flexible. Which
yeah,
is
it's
right?
okay. Correct.